Having studied some basic terminologies related to constraint optimization, let us deal with equality constraints, which means I want to minimize my objective function f of x subject to the constraints satisfying with equality. So, bear in mind the geometry of the problem that we are looking at intersection of the constraints with the objective, and over the points we optimize the objective function. So, let us see how this can be done through an illustrative example, and from there we will derive the theory how to set up the Lagrangian. Okay. So, we would like to minimize the function x1 plus x2, where x1 and x2 are real numbers, right. It is the geometry is basically in 2 dimensions, subject to constraints on x1 and x2. So, the constraint here is x1 square plus x2 square equals a square, that is they lie on a circle. Now, my objective is f of x, x is a vector, it is a 2 dimensional vector, which is equal to x1 plus x2, and the constraint Ci, I will omit x for ease of notation. Ci is x1 square plus x2 square minus a square, that belongs to the equality constraint. I mean, this is x1 square plus x2 square minus a square equal to 0, and that belongs to the equality constraint. Now, to get a feel for this problem, right, if we were to think about the geometry of the problem, I have the circle here, the equation of the circle is x1 square plus x2 square equals a square. It is a circle centered at the origin, so I will just indicate the center here, and it is of radius A, okay, centered at the origin and of radius A. Now, if you even compute f of x equals x1 plus x2 over different quadrants, you can get a feel for this problem. When x1 and x2 are in the first quadrant, in the first quadrant x1 and x2 are positive, right. When they are positive, f of x takes strictly positive values. When I am in the third quadrant, x1 and x2 take negative values, so both of them take negative values, so the sum is going to be negative. And in the other 2 quadrants, I can have x2 to be positive and x1 to be negative in the second quadrant, and it is a flip, x2 is negative and x1 is positive in the fourth quadrant. So, therefore, the sum is sort of, it can be positive, negative, depending upon how my conditions are on x1 and x2, right. So, clearly, if I have to minimize this objective function x1 plus x2, that is the sum of the coordinates subject to the points lying on a circle, then I have to look into the third quadrant, because that gives me the minimum solution, that is where the minimum lies, right, where x1 and x2 are both negative. Again, by virtue of geometry, we can say that if we are in the first quadrant, you will have the maximum value for the objective, because both of them are positive. So, let us compute the gradient of the objective and gradient of the constraint, and then see how this works out for us. Now, I do a del f. So, I take the partial derivative. So, del f is basically the partial derivative of this objective with respect to x1, and then the partial derivative of the objective with respect to x2, that is how I compute. So, this is basically, I write it down here carefully, del f is day by f upon day by x1 and day by f upon day by x2. This is how I would compute. So, I do the math, it is straightforwardly the vector 1, the vector with coordinates 1 and 1. So, therefore, the direction of del f irrespective of the point would be at 45 degrees with respect to the origin, right. It is the unit vector is going to be 1 upon root 2 1 comma 1. So, this is the direction pointed by the red arrows. Now, at the point of the maximum and the minimum, anywhere del f points in this direction. But let us see how del c would be. Now, del c again is the vector that can be obtained by taking the gradients with respect to the coordinates in the constraint equation, right. I write it here for clarity. Del c is basically day bar c upon day bar x1 and day bar c upon day bar x2, right. I just have one constraint. So, I really do not need this I here, right. This is the constraint. Now, the gradient clearly, if you take the partial of this constraint with respect to x1, I get 2x1 and the partial with respect to x2 is 2x2. So, the gradient of the constraint depends on the points x1 and x2, right. It depends on the coordinates x1 and x2. Now, we have a feel that the points minus a upon root 2 and minus a upon root 2, I mean the points with coordinates minus a upon root 2 and minus a upon root 2 and this other point which is a upon root 2 and plus a upon root 2. So, there are 2 points here. So, point P1 is this point a upon root 2 and a upon root 2 and point P2 is this point minus a upon root 2 and minus a upon root 2. They are antipodal, which means at these 2 points P2 happens to be the minimum solution and P1 happens to be where the objective is maximum. Let us see how the gradients are over these points and if we can get some sense as to how we can go about choosing our direction to get the minimum solution. Right, when I evaluate the gradient of the constraint at point P2 which is the minimum solution, I get minus root 2a and minus root 2a, these are the 2 coordinates. Now, similarly when I evaluate the gradient of C at the point P1, I get plus root 2a and plus root 2a. What is important to visualize here is the arrows that I have in green, that is at the point P2 the gradient is pointing in the downward direction here and at point P1 it is in this upward direction and they are just in opposite directions, right. So, this is an important observation here and I can, let us say I start at point a comma 0 which is on the x axis, in the x1 axis, and the arrow that I have here in black, which indicates the clockwise direction, this is how I have to go towards my minimum, or this is the minimizing direction. Now, two questions can come to our mind, right? How to choose the minimizing direction? Second, are there any relationships between this minimizing direction with respect to the gradient of the constraint and the objective, right? And is there some sense of relationship between these gradients and then the minimizing direction, and in general how can I set up, how can I in what direction should I go towards getting the minimum, right? A point to note is just computing del f does not suffice for the minimum, because you have to examine del square f at that point. Computing del f can give you the saddle points, but once you compute the saddle points you need to compute del square f, and at that point you have to evaluate del square f, and then you have to figure out if it is positive, semi definite or not, and then figure out accordingly what whether it is a minima or maxima or these details. Okay. Now, from the figure here, del f star is some scalar multiple of del c evaluated at x star, right? X star is my saddle point, and since I am at the minimum, lambda 1 star happens to be minus 1 upon a root 2. This is straightforward to verify. So, I just take del f, take del c, and then just figure out the scalar constant that links these gradients, because del f is a constant and del c has the symmetry, and you can compute this lambda 1 which is a term, a scalar that can link del f and del c. Okay. So, note that del f is a scalar multiple of del c at the point of maxima as well. So, this is a very important observation, right? The sign possibly flips, the sign flips here, right. So, in one case it is minus 1 upon a root 2, and in the other case for maxima it is going to be symmetrically plus 1 upon a root 2. So, del f is a scalar multiple, but the sign on the lambda is different. Okay. But that is not, I mean, in this case it happens to be the case, that itself is just not enough for us to invoke and figure out if this is maxima or minima. So, we have to do the analysis further to figure out whether the saddle point is a minima or a maxima. So, in order to proceed further with our analysis, let us analyze this issue through a Taylor series expansion around the constraint. So, this is what we want, because at the local vicinity we have to take a gradient, because the gradient will tell us the direction how we need to go through our objective function, and therefore, we have to see the link with this direction, the gradient of the objective and the gradient with respect to the constraints, and link all of them in some clever way so that we can analyze this situation. Now, C of x equals 0, because this is the equality constraints that we are dealing with. Now to maintain feasibility with respect to this equality constraints, with respect to the equality constraint C of x equals 0, I choose a direction D, which is a vector here, and C of x plus D is 0. Now what I do is I expand C of x plus D, that is in the small vicinity around x, because I have to be still feasible in around that point. So I look at a small direction D there. Now C of x plus D, by expanding using a Taylor series up to a first order approximation, I get this quantity C of x plus D is approximately equal to C of x plus the gradient of C with evaluated at x transposed times vector D, right. This is basically an inner product between del C and the direction. Of course, if you are wondering how to do the Taylor series expansion with respect to vectors, you can look into any calculus book for doing this, but be aware that C of x is a scalar quantity, right. So therefore I have this is the inner product gives me a scalar, so at least this is obeying with respect to the dimensions. Okay. Now C of x plus del C transposed D equals 0, but C of x equals 0 because this is our equality constraint. So we will end up with this important equation, that is del C transposed D must be equal to 0. I call this equation A. So what this means is, if I have del C pointing in some direction evaluated at x, and I have a direction D that I have to choose, they have to be orthogonal, right. This is sort of implied from this equation. Similarly, the direction of optimization must produce a decrease in the function f. That is, f of x plus d minus f of x must be less than 0, right. I have f of x, I compute f of x plus d, right. F of x minus f of x minus f of x minus f of x plus d is greater than 0, right. So this is sort of straightforward. Now by doing a Taylor series expansion around x using a first order approximation exactly in the same way that we did earlier, right. You have f of x plus d is approximately, so I will write this here, this is f of x plus del f times dot d, right, and I subtract f of x. So I will end up with the gradient of f dot d, that is the inner product of the gradient of the objective and the direction, and that has to be strictly less than 0. Now if there exists a direction D that satisfies this inequality that I call equation or inequality B, I call this I number this as B, that satisfies B and A, right. A is this where C and D are orthogonal, that is del C dot D is 0, and then that satisfies this inequality constraint, that is del F transpose D is less than 0, then we can see an improvement towards our solution, right. That means we are getting better. Now there are two cases to consider here. The first case is such a direction does not exist or exists, because if it is a single direction, right, a single direction is what we want. We do not want to have multiple directions that can confuse the algorithm, because we want to have a unique direction that we want to take. So such a direction does not exist, and the other case is such a direction exists. So let us look into case 1. When such a direction does not exist, that means I am somewhere at the saddle point. Del F and del C are scalar multiples of each other. That means they can be aligned in the same direction or they can be in opposite directions. So what this implies is del F is some lambda times del C, and this picture was sort of clear when we looked at minimizing of x1 plus x2 subject to x1 and x2 lying on a circle, right. Now why this is an important result? When del F equals lambda del C, equations A and this inequality B, I mean equation A and inequality B do not simultaneously hold. This is important, because one says del C transposed D is 0, the other says del F transposed D is less than, strictly less than 0. So I can't have something which is strictly less than 0 and then something when it is equal to 0, and that can happen when del F is lambda del C. So you just plug this, instead of del C you replace it by instead of del F just replace it by lambda del C and proceed with when you plug in into equations A and inequality B, and you can infer that they do not simultaneously hold. So what we do is we form a Lagrangian, because when you look at the constraint optimization problem, we form the Lagrangian L equals some F plus minus lambda C, that is F is my objective and C is my constraint equation and lambda is the Lagrange multiplier. Now when you take the gradient on the Lagrange and set it equal to 0, because this is where we have to solve for our saddle points, then del F is equal to, I just transpose, I put the lambda C on the other side, I get minus plus lambda C. What this means is the sign of the constraint in the Lagrangian does not matter. I can put a plus sign or I can put a minus sign, and I can have this minus plus lambda, I mean del F is equal to minus plus lambda C. So it does not matter regarding the sign. So sign does not matter. And irrespective of whether I put a plus sign or a minus sign before my constraint, I still will land up with the saddle point, and from the saddle point I can compute my Hessian post that, and I can infer whatever I want to do from there, whether it is a minima or a maxima. Okay. So, this is a very important detail. So, when you formulate the Lagrangian for the equality constraint, the sign before the constraint in the Lagrangian does not matter. Just choose a Lagrange multiplier lambda, right. Typically you can set up lambda to be, you have to solve for lambda as well. So, the sign before this lambda c does not matter. You can choose plus 1, plus 1, or you can choose a plus or a minus, but when you take the derivative, because you are satisfying del f to be equal to plus minus lambda del c, it does not really matter. Okay. But this issue of sign can be pronounced for an inequality constraint, and let us see how the derivation can be obtained. So, what we have from this is we can arrive at a saddle point, and we still have to infer the sign of the Hessian to proceed for assessing the validity, whether it is a minima or a maxima. Now, so far we discussed the case when there is no direction, right. There is no direction that we are at a minimum point, and what really happens at that point. So, the geometry led us to the fact that del f equals lambda del c, where lambda is some scalar multiple, it can be positive or negative. Now, when we are optimizing, there should be a direction that should exist. So, let us see what is the direction and how we can analytically get the solution, and how we can verify that this direction satisfies the conditions given in equations A and B. Okay. Now, when such a direction exists, that means we have not reached the saddle point yet. A solution to D can be obtained as follows: D is equal to negative of the identity matrix minus del c times del c transposed upon norm of del c square, this whole thing times del f, right. Del c times del c transposed gives me the outer product, which is my matrix, and I am subtracting, and norm of del c square is a scalar. So, I have subtraction of these two matrices in the direction of del f. So, you may wonder, this equation 1 that I wrote, if how did we even arrive at it, but let me verify first that this equation 1 satisfies my equation A and inequality B, and in the process of verifying this, you may get an insight how to get this direction D. Now, D equals, I just expand this out. So, I times del f is del f, there is a negative sign sticking out, it is a minus del f. So, the negative and the negative is a positive here. So, it is going to be del c times del c transposed times del f upon norm of del c square, and norm of del c square can be written as the inner product of del c and del c, right. It is del c transpose del c, this is the inner product. And here this is the outer product. Now, let us consider equation A. So according to equation A, del C transposed D has to be 0. So I have a solution to D given by this equation in Roman numeral 1, right. So let us see if this is valid. So what I have to do is plug in D there and then take the inner product of D with del C, right. So del C transpose D is going to give me minus del C transposed del F plus I have del C transposed. So if you just see this equation before, it can help you. So I pull this del C transpose here, del C transpose times del C times del C transpose times del F upon this. Now del C transposed del C is a scalar, which is, see, if it is, if they are matrices, I cannot cancel them out. This is very important. So I mean, any graduate student would realize this immediately, but if there are any that are confused, so this is basically a scalar and therefore I can cancel this out, because if they are matrices then I cannot cancel like this. So they are scalars, I can pull them out. So therefore what I land up is minus del C transpose del F plus del C transpose del F, and this happens to be 0 trivially, right. So therefore equation A is satisfied. Now let us consider the inequality which is B, which is del F transposed D is what I need to compute. So I plug in D here, given by del F minus del C times del C transpose del F upon norm del C square. So I do the simplification, I get negative del F transposed del F plus del F transposed del C times del F transposed del F. So it is del F transposed del C times del C transposed del F upon norm del C square. Okay. So if you are savvy, you will realize that this first term can be realized as del F, the norm of del F square, right, with a negative sign. Now del F transposed del C times del C transposed del F can be realized as norm of del F transposed del C squared. Now in the denominator we have norm of del C square. So this is second term, so I will just indicate it slightly carefully here. What we have to observe is just get a feel for these quantities del F and del C that I have written down here. Now with the simplification, this term minus norm del F square plus norm of del F transposed del C square upon norm of del C squared is like this is basically Cauchy-Schwarz condition, and from Cauchy-Schwarz inequality this quantity happens to be less than or equal to 0 with the equality when del F equals lambda del C. But the condition for equality is ruled out because we considered that in case A, therefore del F is not equal to lambda del C. Therefore this is going to be a strict inequality, right. The equality is ruled out, it is a strict inequality. So D is indeed the correct direction because it satisfies the constraints that we have. Okay. So, D is the correct direction because it satisfies the constraint that we have. So, this gives us an important perspective to our geometry of this problem. So, at the saddle points del f happens to be lambda del c, and if it is not at the saddle point, you can choose a direction D given by this equation, which is minus identity plus this del c times del c transposed upon norm del c square times del f by this equation, which is 1, and then proceed in that direction towards whichever algorithm that you are interested in, such as gradient descent, etc., and then get towards a point of optimality. Right. This is very, very important, because given the gradient of the objective and the gradient of the constraint, right. So, there is a direction D when you are trying to optimize this problem, and no direction exists when you are reaching the saddle points. Okay. So, with this we stop here with the equality constraints, and then we will look into the inequality constraints.